Okay, so here we have a problem on electrochemistry. Based on the standard reduction potentials in the table above, what is the value of E cell? Right, we're looking for this value for a standard galvanic cell made with silver and chromium half cells. So we are given these half reactions. When silver plus is reduced, we get this 0.8, and when chromium 3 plus is reduced, we get this negative 0.41. So how do you get E cell? This is going to be E cathode minus E anode. So the cathode is where the reduction takes place. The anode is where the oxidation takes place. And this is actually very, very, very simple. It can't get any easier than this. All you do is you take the more positive value. That is a greater reduction potential. That means it is more favorable. The reduction is more favorable. And so whichever one has the higher value right here, that is going to be the reduction. That is going to be what occurs at the cathode. And so that means the other one is the anode. And all we do, this is all it is just E cathode minus E anode. That's all it is. You plug it in. We don't have to worry about, all we have to do is identify which one it is. So again, the cathode, the more positive value. So if you have a positive and a negative value, it's the positive value. The positive value is going to go right here with the cathode. Or if you have both positive or both negative, it's whichever one is greater. So if they're both negative, whichever one is closer to zero. If they're both positive, whichever one is bigger. So whichever one is the bigger number, that is going to be E cathode, and it's just E cathode minus E anode. You don't have to worry about the number of electrons. We don't change anything whatsoever. We don't have to worry about the fact that this is a reduction potential and this is actually getting oxidized. That's what this minus sign is for. It takes that into account. And so if we do E cathode minus E anode, definitely watch your arithmetic. We're subtracting a negative number, so we're actually adding it. We're going to get 1.21 volts. So once again, you're definitely going to see these, right? We do need to be able to calculate E cell for a galvanic cell, and we're just, once again, the greater reduction potential, that is the reduction, that is what's occurring at the cathode, where the electrons are delivered to reduce the ions, and the other is the anode, and it's just E cathode minus E anode. End of story. That's your E cell. So that's a quick one on electrochemistry. Okay, here's a question pertaining to galvanic cells. This says, which of the following best accounts for the fact that a galvanic cell based on the reaction represented above will generate electricity? So we have chlorine gas and iodide ions yielding chloride ions and iodine gas. Or I2 rather, in aqueous. And so here are the options. Cl2 can easily lose 2 electrons. Cl2 is a stronger oxidizing agent than I2. I atoms have more electrons than do atoms of Cl. Iodide is a more stable species than I2, and I2 is more soluble than Cl2. So what do we want to try to focus on here? So this is a redox reaction, right? So first let's identify the players. We've got Cl2, that's elemental, so that's 0, going to Cl minus, -1. So that is the reduction. And then iodide starts at -1 and goes to 0. So I minus is getting oxidized. So it is the reducing agent. And Cl2 gets reduced. So it is the oxidizing agent. Now, they're telling us that this generates electricity. So this is favorable. This is a favorable process. If this were not favorable, it would go the other way, right? One of these is a stronger oxidizing agent, right? If we were to reverse this, then I2 would be getting reduced and would therefore be the oxidizing agent, right? If we were going from I2 to I minus, right? That would be the reduction, and so that would be the oxidizing agent. But it doesn't go that way. It goes the way that is depicted. So clearly, Cl2 must be a stronger oxidizing agent than I2 because this electron transfer could go either way. But one will be more favorable than the other, and that will be the spontaneous direction. And it is a spontaneous redox reaction that is held within a galvanic cell to generate a current. Right, so this is definitely going to be B. Cl2, so first of all, we had to recognize, always when you have these, it's good to point out where the oxidation is taking place, where the reduction is taking place, and therefore which are the oxidizing and reducing agents, because then we're set up to answer whatever the question is asking, right? It is inevitably going to have some of this terminology. We have to identify certain things. And then looking at these, right, the rest of the answers, they just don't really work, right? Cl2 can easily lose 2 electrons. Well, it can't really easily lose 2 electrons. Also, it's not doing that, right? It is the one that is gaining the electrons because it is getting reduced. So that just doesn't make sense. And the rest of these, right, iodine atoms have more electrons than chlorine atoms. Well, yes, they do, but that doesn't really have anything to do with this, right? We're talking about electron transfer and which one will more readily transfer electrons. Iodide is a more stable species than I2, not really. Solubility, we're not looking at solubility. We're looking at electron transfer. We're looking at reduction potentials and which one of these is going to be, which direction is more favorable, right? This one is spontaneous, so this is more favorable because Cl2 is a stronger oxidizing agent than I2. If I2 were stronger, this would be going in the opposite direction, right? So this was a good one about just galvanic cells and making sure we understand the logic behind a galvanic cell. Okay, we've got a couple questions here regarding thermodynamics. So we have some conditions for change in enthalpy and change in entropy, and we want to assign them to these statements. So the first must be true for a reaction that is spontaneous at all temperatures. So when we see the word spontaneous, when we are talking about spontaneity, we know we are talking about delta G. We're talking about Gibbs free energy. Right, so we want to make sure we have that association. Spontaneity, we're talking about delta G, and that is equal to delta H minus T delta S. Now, if something is spontaneous, that means that delta G is negative. And in order for, so we have this temperature term right here. And so we know that if it is a situation where we have, it is enthalpically favorable but entropically unfavorable, or enthalpically unfavorable but entropically favorable, then temperature matters. A high or low temperature can determine whether it is spontaneous or non-spontaneous. But this says spontaneous at all temperatures, so no matter what T is. So in order for delta G to be negative, no matter what T is, delta H must be negative and delta S must be positive. So it's exothermic, it releases energy, and it's entropically favorable. It involves a further dispersal of matter or energy. And so if you have a negative minus a positive, it does not matter what T is. T could be close to absolute zero, or it could be a million. It doesn't matter. You will always have a negative minus a positive must be negative. Delta G must therefore be negative. So where do we see delta H as less than zero and delta S as more than zero? That would be this one. So number 1 is C. Okay, number 2, true for the evaporation of water at ambient conditions. So what is happening when water evaporates? So first of all, evaporation, we have to know that means it's a phase change. We're going from the liquid phase to the gaseous phase. So what is happening when we go from the liquid phase to the gas phase? Water molecules in the liquid phase, they're sloshing around and they're making hydrogen bonds, right? They're making these fleeting electrostatic interactions as they move around, and it is required that a certain amount of energy be supplied to overwhelm those hydrogen bonds in order to liberate the water molecules into the gas phase, right? By making those hydrogen bonds, the system goes to a lower energy. So in order to go from interacting to not interacting, where in the gas phase they're all very far apart and not making hydrogen bonds, this much energy must be supplied, right? Water molecules separate, water molecules hydrogen bonding, lower energy. So this energy must be supplied. So that means that evaporation is endothermic, right? Energy must be supplied in order to liberate the water molecules into the gas phase. So delta H must be positive. But what's going on entropically? We know that phase changes going from solid to liquid to gas are entropically favorable. They have a positive delta S because it's a dispersal of matter. We're going from the liquid phase to the gas phase where they are spread out. So evaporation is entropically favorable. So we have a positive delta H and a positive delta S. So that has got to be A right there. And then finally, true for the combustion of liquid pentane, that's C5H12, in the liquid form to form water vapor and carbon dioxide gas at 1 atmosphere. So, speaking in terms of enthalpy, we should know, just logically speaking, that a combustion reaction is exothermic. A combustion reaction releases a lot of energy. That's why the combustion involves fire and explosions, right? So combustion is certainly exothermic, so we're going to have a negative delta H. And then what about entropy? So, well, we're taking this and oxygen, and then we're forming water and carbon dioxide. So we could write that out and balance it and everything, but instead, it's even much simpler than that. We can notice that we are going from a liquid, right? We have liquid pentane, and we are forming water vapor and carbon dioxide gas. We're forming gaseous products. So again, just like in number 2, we're going from predominantly liquid, oxygen is a gas, but we have liquid pentane, to strictly gaseous products, right? So that certainly is entropically favorable. So enthalpically favorable, entropically favorable, we have a negative delta H and a positive delta S. That means, once again, we are looking at C. So we've got CAC. So this is a nice problem, making sure that we understand delta H, what positive and negative values mean, delta S, what positive and negative values mean, and how they correlate with delta G, so that we can talk about these various processes and understand qualitatively what is going on. So we have one on electric current. So these ones can be a little confusing, but if you just remember what all of this terminology means, it can make things a lot simpler. So this says an electric current of 1 ampere is passed through an aqueous solution of nickel nitrate. How long will it take to plate out exactly 1 mole of nickel metal, assuming 100% current efficiency? So what does this all mean? An electric current of 1 ampere, remember amperes are coulombs per second. So this is 1 coulomb per second. We're talking about, in this context, plating out 1 coulomb of electrons, or we're talking about the charge. We're talking about charge here per second. So 1 coulomb of charge per second. And then we need Faraday's constant. Faraday is telling us that it's 96,500 coulombs per mole of electrons. And so we want 1 mole of nickel metal. Now we have to look at the charge of the ions. So with nickel nitrate, this is actually Ni2 plus and 2 nitrates, right? The nitrate is -1. So we do have to know the charges on these ions. Nitrate is minus, and there's 2 of them, and so nickel is 2 plus. So if we want to plate out 1 mole of nickel metal, we want to plate out 1 mole of nickel 2 plus ions, meaning it needs to be deposited onto the metal. It has to be neutral. So it's basically saying how we need to neutralize 1 mole of nickel 2 plus ions. So we need 2 moles of electrons to do it, right? We need 2 moles of electrons. Because each ion needs 2 electrons, and we need a mole of those ions to get a mole of nickel metal. And so Faraday is saying that it's 96,500 coulombs per mole of electrons, and we need 2 moles of electrons, right? Remember, it's 1 mole of nickel metal, and so that's why we need 2 moles of electrons, 2 electrons per ion. So all we need to do is take 2 times 96,500. Right? Because that is going to give us 193,000 coulombs, right? So 193,000 coulombs is the charge associated with this operation, and they're making it nice and easy for us. 1 ampere is 1 coulomb per second. So if it's 193,000 coulombs and it's 1 coulomb per second, it's going to be 193,000 seconds to achieve this process here. So ampere, we do need to remember, right, all of these units on these parameters, coulombs per second, that's useful to know. We did have to know there were 2 electrons per nickel ion in order to achieve this. 1 mole of nickel metal, and then they gave you Faraday's right there. We have to remember what that is, what that means. It's the charge associated with 1 mole of electrons. So that was a short one on electric current. So here's a quick one on entropy. Delta S will be positive for which of these reactions? And so a change in enthalpy, change in entropy. Remember that a change in entropy is associated with the dispersal of matter and energy. And when delta S is positive, that means an increase in entropy or greater dispersal. You can think of it as more randomness or more disorder, but I think dispersal is a better term. So when delta S is positive, we have a greater dispersal of matter and energy. So which of these reactions achieves a greater dispersal of matter? So we have to look at the number of moles of particles, and we also have to look at phases, right? So here we have 2 moles and 1 mole yielding 2 moles. So that means molecules came together to generate fewer molecules. So that would be a decrease in the dispersal of matter. So that's not it. Here we had 2 NO2 yielding 1 mole of N2O4. Again, this is a synthesis reaction. This is starting with more particles and ending with fewer particles. So there is a less of a dispersal of matter. So that one does not work. BAF2 solid going to barium 2+ and 2 fluoride ions. This is great. So this is dissolution. We're going from an ionic solid. We're going from a lattice structure to aqueous ions in solution. So the solid lattice has dissociated and all the ions are now floating around. That's definitely an increase in the dispersal of matter because we have this nice neat ordered lattice, and now the ions are all scattered around and solvated by water molecules. So that is it. Let's just look at the other ones as well. Here we have mercury and O2, an oxygen gas going to make HGO. And so this is terrible because we're going from 3 moles to 2 moles, and we're going from liquid and gas to the solid phase. Remember, going from solid to liquid to gas, entropy is increasing, and going from gas to liquid to solid, entropy is decreasing. So both because of stoichiometry and the phases, this is a bad answer. And then here, CO2 gas to CO2 solid, we have the same number of particles, but they're going from the gas phase to the solid phase. Gas phase, they're scattered around. Solid phase, they're compacted. This is deposition. Deposition is certainly entropically unfavorable. So that is going to have a negative delta S. If it was going from solid to gas, that would be positive, but in this case it is not. So when we had to number 1, remember that a positive change in entropy means an increase in entropy, right? So number 1, we had to know what a positive delta S meant. But once we recalled that a positive delta S meant an increase in the dispersal of matter, we just had to look at which one achieves an increase in the dispersal of matter. So the dissolution of this ionic solid was the answer, and that's that one. Okay, we have one here on spontaneity. We're talking about delta H, delta S, which means we're also talking about delta G. Here we have this reaction. We have this positive delta H, meaning it is endothermic or enthalpically unfavorable. And we have this delta S, which is also positive, which means it is entropically favorable. And so we want to know if this reaction is spontaneous, non-spontaneous, under which conditions. And so with spontaneity, we are always talking about delta G. Delta G, or change in Gibbs free energy, is the parameter that is telling us whether a reaction or a process is spontaneous or non-spontaneous. Negative delta G is spontaneous, positive delta G is non-spontaneous. And this is going to be equal to delta H times T delta S. Now, we are given a positive delta H. So that's there, and we're given a positive delta S. Now, this reaction is, we'll look at the options. Okay, unreliable, that doesn't mean anything at all. So quickly, we're going to just get rid of that one. That doesn't make any sense. So spontaneous, non-spontaneous. Can we say that it is spontaneous or non-spontaneous at all temperatures? Well, let's take a look. We have a positive value minus a positive value. Well, a positive minus a positive could end up being positive or negative. If we have a big positive minus a small positive, it'll stay positive. If we have a small positive minus a big positive, that's enough to get it into negative territory, and you'd have a negative answer. And so we know that it is going to be spontaneous only under particular conditions that have to do with temperature, right? And so we want to know what are the temperatures at which this becomes spontaneous. Now, in order to get delta G negative, because a negative delta G means spontaneous, we need for this second term to be bigger than the first term. So delta H, a positive, minus a bigger positive would get us into negative territory for delta G and make it spontaneous. And the way we get this term to be as big as possible is to have high temperatures, right? The bigger T is, the bigger this term is, and the greater probability that this will become negative as a whole. A positive minus a bigger positive gives you a negative overall. So with this, as we have it here, it must be spontaneous only at high temperatures. Precisely what temperature, we're not sure. We would have to go and do a calculation. We don't need to. It will suffice to talk about this conceptually right here. But that is very important. We definitely need to be able to talk about the Gibbs free energy equation and how delta G relates to delta H and delta S and temperature. You will definitely see problems like this on the exam. So we have to be very comfortable knowing what positive and negative delta H values mean in terms of endothermic, exothermic, enthalpic favorability or unfavorability, and positive, negative delta S values, entropic favorability, unfavorability, what those mean, and then how to put them into this equation to predict spontaneity. So that was a very good one on spontaneity.